Hello, my name is Thomas Yore, and I'm doing my final report on the Michaelis-Menten equation. So what is this equation used for? As drugs metabolize in your body, many enzymes help speed up each step of the reactions. Substrates are the substances that react with these enzymes. Now, I'm sure most people know what enzymes do, but how do we quantify the rate of the enzyme's reactions depending on substrate concentrations? Well, this is the exact purpose of the Michaelis-Menten equation. The equation is dC over dt equals negative Vm times C divided by Km plus C. It is made up of four different ordinary differential equations that are summed up into this one final equation, and it is an approximation. Now, the limits of this equation. When this differential equation is integrated, it needs to be in a specific situation. Only one metabolite must be formed, and a metabolite is an intermediate or end product of a metabolic reaction. They also assume a single open model because it is also assumed during this reaction the system between the enzyme and substrate are in steady state. Parameters of this equation. Vm is the maximum rate of reaction in units of moles divided by meters cubed in seconds. Vmax is proportional to the amount of active enzyme present. Now, Km. Km is the Michaelis-Menten constant and is in units of moles divided by meters cubed. Km is equal to the reactant's concentration when dC over dt is equal to the maximum velocity divided by 2, and is also independent to enzyme concentration. dC over dt refers to the change of substrate concentration in units of moles divided by meters cubed in seconds. dC dt is also referred to as the volumetric flow rate of the enzyme substrate complex. And C is the substrate concentration in units of moles divided by meters cubed. Below is a block diagram and graph of the Michaelis-Menten equation. The values for the parameters used in Simulink were Vm equals 0.22, Km equals 0.1, and initial concentration of 0.5 was used. The simulation was run for 20 seconds. Now, let's look at the relationships between the parameters. How changes in the Vm parameter affect the graph. The Vm value increased to 0.5. When it was increased to 0.5, you could see that the substrate concentration decreased at a much faster rate. Whereas when the Vm value decreased to 0.1, this caused the substrate concentration to decrease at a slower rate, which makes sense because the faster the velocity between the substrate and the enzyme, the faster those reactions will be done. How changes in the Km parameter affect the graph. When the Km value was increased to 0.3, it took longer for the substrate concentration to decrease. But when the Km value decreased to 0.05, it actually took less time for the substrate concentration to decrease. And after looking at the relationship between Km and Vm, it becomes apparent that they have an inverse relationship. So when one increases, the other decreases. Now, looking at the changes in the initial substrate concentration and how it affects the graph. So this graph has many different substrate concentrations, initial substrate concentrations, and how the graph looks with each one of those different initial values. And the initial substrate can be seen on the y-axis of the graph when time equals 0. This graph also shows how the changes to the initial substrate concentration can make it where the higher the initial concentration is, the longer it takes for the substrate to fully react, all the substrates to fully react with the enzymes. And here are my references that I used for this project. Thank you for your time. I hope you enjoyed it.